So the graph of a quadratic function is not a straight line, but it has a specific shape, and that shape is what we're going to look at next. We're going to start with just kind of the most basic quadratic function, f of x equals x squared. And of course, that equals 1 times x squared plus 0 times x plus 0. And so this is a quadratic function because it fits the form with a is 1, b is 0, and c is 0. Here we've got a bunch of values for x. We need to find the values of f of x because those are going to give us our y coordinates. So we'll take -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So notice these y values come down and then go up again. And notice the changes, right? We decreased by 5, decreased by 3, decreased by 1, then increased by 1, increased by 3, and increased by 5. -5 plus 2 is -3. -3 plus 2 is -1. -1 plus 2 is 1. 1 plus 2 is 3. 3 plus 2 is 5. So the values of y that we get here really do fit that change in the change is constant pattern that we said we expected for quadratic functions. What does this graph look like? Well, when x is -3, y is 9. When x is -2, y is 4. When x is -1, y is 1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. When x is 3, y is 9. So we see that we have this curve that comes down and then comes back up again in kind of a U shape. So I'm going to sketch this now. It's flat at the bottom, not pointed. And then it just kind of comes up smoothly through all the points and then continues on. So just going to sketch it coming up smoothly through all the points and then continuing on. So that shape has a name. That shape is called a parabola. Now, a parabola is a specific geometric shape. Not every U-shaped curve is a parabola. Every U-shaped curve we're going to get in this class is a parabola. But there are plenty of graphs that are U-shaped that are not parabolas. It's a parabola if it comes from a quadratic function. And so that's how we're going to recognize that these are, in fact, parabolas here. Now, a parabola might be U-shaped, or it might be upside down. It might be N-shaped. The U-shaped parabola is said to open up. The N-shaped parabola is said to open down. There's a special point on a parabola called the vertex. The vertex is the point where the parabola turns. So in a parabola that opens up, the vertex is at the bottom. The parabola will open up if the x squared term is positive. And then the vertex is at the bottom So the y value at that point is the minimum value of the function. If the parabola opens down, which is going to happen when the x squared term is negative, then that point is at the top. And so the y value of the vertex is the maximum value of the function. The last piece of the anatomy of a parabola we're going to mention is that if we draw a vertical line through the vertex, the parabola is symmetric across that line. So if we pick the parabola up and flip it across that line, it looks exactly the same. That vertical line then is called the axis of symmetry of the parabola. And so here's just kind of a sketch of the anatomy of a parabola. If we have a parabola that opens up, the vertex is here at the bottom, and then the parabola goes upward symmetrically on either side of that. If the parabola opens down, the vertex is here at the top, and then the parabola goes down symmetrically on either side of that. So we can just look and see the parabola if we have the graph of a quadratic function. Now, we can tell by looking that this graph represents a function because it passes the vertical line test. You can see just all the vertical grid lines only cross at once. Right? And if we drew any vertical line in between, that would also only cross the graph once. How do we know it's a quadratic function? Well, because it's parabola shaped. Now, not every U-shaped or N-shaped curve is a parabola, but all the ones we see in this class will be. And after you've seen a few parabolas, you start to be able to recognize, yeah, that's parabola shaped, or, oh no, that's not quite parabola shaped. For purposes of this class, if it's a curve with a turning point, it's probably a parabola. And then this is just the graph of a function. So we can use it to answer questions about the function. For example, if we want to find f of 4, we're given the input 4 and asked to find the output. So we want to find the y value for the point on the graph whose x value is 4. So we find the 4 on the x-axis, we go up to the graph, we find this point, we see that its y-coordinate is 3. So f of 4 is 3. Similarly, to find f of 2, we have input, so x value of 2. We want to find the output, so the y value. We find the 2 on the x-axis. We go up and find the graph. We go over and we see that its y-coordinate is 5. This is the point 2, 5. I'm labeling it because we're going to find it again. F of 2 is 5. Now, this is something that's new for parabolas. We're going to find all the numbers that we can put into this blank. So we're finding x values that go with y value -3. Here's the -3 on the y-axis. And what we notice here is that there are 2 points on this graph that have y value -3. Let's see. So this point, no label over here, but it looks like every box is 1. So this will be -2. Over here, we've got 2, 3, 4, 5, 6. So when x is -2, y is -3. When x is 6, y is negative 3. If we were just asked for one value that could go in that blank, we could say negative 2, or we could say 6. Either one would be correct. Remember, for a function, every input can only give one output, but the same output can come from more than one input. For quadratic functions, the normal thing is for a particular output to come from two different inputs. Okay, this is just a graph. So we can talk about the normal graph things. We can say, what's the y-intercept? The y-intercept is the point where the graph crosses the y-axis, which is right there. The x-coordinate is always 0. And then we've already read this y-coordinate, it's 3. So the y-intercept is at the point 0, 3. We can also look at the x-intercepts. That's the place where the graph crosses the x-axis. And we see that that happens twice. There are two x-intercepts. A function can only ever have one y-intercept because the y-axis is a vertical line. If the graph crosses it twice, then we're not looking at a function. But a function can have as many x-intercepts as it wants. Quadratic functions will typically have 2. And these ones appear to be at fractional points, right? The graph crosses the x-axis once between -2 and -1. And then the next one, it crosses the x-axis again between 5 and 6. So we can't exactly read the coordinates of the x-intercepts in this specific example. Sometimes we get lucky, they happen in a neat grid line. And we will get techniques later that would let us find the actual x-coordinates to as many decimal places as we want. For now, though, just by looking, we can see that one of them is between x's -2 and -1. The other one is between x's 5 and 6. Last point. Vertex of the parabola is at 2, 5. It's that point at the top. And we already wrote down the coordinates because that happened to be this point that we were asked for. Okay, so that's how we do this with a graph. If we have a table of values, we can't see the parabola, but we can still think about what the points on the graph would look like just from the table of values. So here we have a table of values with input x and output y equals f of x. We can tell that this represents a function because each input only appears once. To tell that this represents a quadratic function, we need to look for the quadratic pattern. So we need to be able to say the change in the change is constant. So let's see what the change in the change is. First, we'll find the change going from one point to the next. 19 to 9, we subtract 10. 9 to 3, we subtract 6. 3 to 1, we subtract 2. And then 1 to 3, we add 2. 3 to 9, we add 6. 9 to 19, we add 10. And then we might need to do subtraction on the calculator for this one. 33 minus 19 is 14. So going from 19 to 33, we add 14. So it looks to me like these numbers are going up by 4. And I can spot that pretty easily for the positive numbers. If I want, I can use a calculator to check that I'm also adding 4 for the negative numbers. So how can we tell that this is a quadratic function? The change in y is constant. And then, again, we can do all of the things that we can do with an input-output table. So if we want to know f of 4, we'll find input 4, find the corresponding output, and we get that f of 4 is 3. If we want to know f of 2, we find input 2, find the corresponding output, and we get that f of 2 is also 3. If we want to answer f of what is 19, we expect 2 possible answers here. And indeed, we find output 19 showing up twice in our table. Once came from input 0, and once came from input 6. We can talk about the y-intercept of this function, even though we can't see the graph. Remember, the y-intercept is where x is 0. We have a row here where x is 0. And so this row gives us the y-intercept. We see that the y-intercept for this function is 0, 19. What about the vertex? Well, to get a candidate for the vertex, we notice that the value of this function is decreasing and then increasing again. So the vertex here is going to be the lowest point. This row is where we have the lowest y value, right? So the outputs decrease from 19 to 1, and then they start increasing again. But it's also possible that the vertex isn't in our table at all. So with that in mind, we also need to check symmetry. What does that mean? Well, remember the axis of symmetry runs through the vertex. What we expect if we found the vertex is that if we go one step on either side, we'll get the same y values. 2 steps on either side, same y values. 3 steps on either side, same y values, and so on as far out as we can go in our table. And that is what we see. So our lowest point is 3, 1, and the symmetry checks out for that to be the vertex. So this vertex, the turning point, is a unique property of quadratic functions among all the functions we're going to study in this course. Linear functions didn't have it. Linear functions either just always increased or always decreased. The other kinds of functions we're going to learn after this also don't have that. They either always increase or always decrease. Having this turning point is the big thing that we want quadratic models for. We're going to often choose a quadratic model because we see that our data have a turning point.